D'acord.
Yeah, it's working.
Everybody, today we are here in order to see the defense of Laia Estrada of her PhD. I think that here with me, I'm Javier Senent. I work as a científico titular in the Desertification Research Center in CSIC in Valencia. Also with me is Loïc Botias from the University of Toulouse, and Ana Menció from the University of Girona. We are going to evaluate, Laia, your thesis and your document. I think that the way we are going to interact with you is in English most of the time. I don't know if perhaps later in the questions we can modify if we need to another language. And we have an agreement that you have around 45 minutes, 1 hour in order to present your work, and then we will have a discussion about some questions about your document. Okay, Laia, so please go ahead and start your presentation.
We can go there and see.
Està vermell. Oh, no, ja se sent, però sí. Good morning, everyone, and thank you for coming to the defense of my PhD, titled Integrating Surface and Subsurface Water Resources in Catchment Modeling to Support Decision-Making. First, we'll begin with an outline of this presentation. I'll begin by introducing my PhD and its objectives, and then I'll follow on with the general methods that I employed. And then I will move on to the results, which are divided into 4 main chapters. And each of these chapters represents either a published paper or a manuscript. Then I'll continue with the general discussion and finally the conclusions. Water scarcity, which occurs when water demand exceeds the water availability in a region, is a worldwide issue that affects many regions of the world, with about half of the world's population being affected by severe water scarcity at least once a month of each year, as we can see in brown in this picture. Just last month, the UN released this report on the left, speaking about global water bankruptcy, because some regions are living beyond their hydrological means to the point that the lack of water resources has become irreversible. And this report highlights the need to mitigate further damage. And also, in this context, it's very important that we have a good understanding of watershed processes and dynamics. When we speak about water scarcity, most people think about not enough water, and that is true. For example, in the Mediterranean, due to its intrinsic climate variability, we can have situations where water scarcity occurs during droughts, naturally. However, human-induced climate change, as well as increased demand due to increased population growth, can also lead to water scarcity. However, even if there is enough water to meet the demand, we also can have situations where we have water scarcity due to other reasons. For example, a bad allocation from the management perspective of those water resources can lead to water scarcity. Most importantly, we have to consider the quality of this water, because it can be too degraded to meet the demands. For example, when we consider also water quality as well as water quantity in order to assess water scarcity, we see that the percentage of population that is being affected and will continue to do so in the future by water scarcity increases significantly. As we can see in this graph, where the dotted lines only consider water quantity and the ones above consider water quantity and quality. In this context, the main objective of my PhD is to develop and implement a watershed modeling approach in order to characterize and assess watershed dynamics. In particular, we consider both water quantity and water quality, and the main goal is to assess climate and management scenarios in order to support sustainable and efficient decision-making. We also have three specific objectives. The first one is to quantify water quantity at the watershed scale, also focusing on the relationship between groundwater and surface water, which will be covered in chapters 1 and 3. The second one is to assess water quality by developing a modeling framework to characterize pollutant fate and generation, fate, and transport. And finally, the third specific objective is to assess management scenarios at the watershed scale in order to support sustainable and efficient decision-making. The basis onto the general methods, the basis of my PhD has been the SWAT Plus model, which is a semi-distributed and process-based watershed model widely used around the world. And here in this flowchart, we can see the main processes that are simulated with SWAT Plus across an entire watershed, including surface and subsurface processes, water quality, plant processes, as well as management operations. In particular, in Chapter 3, we have applied the GW Flow module for SWAT Plus, which represents an improvement in the relationships between groundwater and surface water. And one of the main reasons that this model was chosen for my PhD is because, unlike other commonly used watershed models, this is free to use as well as open source, meaning that it can be easily modified to include new processes and dynamics which were not previously included. To test the developed modeling framework, I have used the Catalan River Basin District as a case study. In particular, depending on the chapter, due to data availability, only several basins have been simulated. For example, in Chapter 1 and 4, most of the Catalan River Basin District are being included. However, in Chapter 2, only the Llobregat, Besòs and Tordera basins are simulated, while in Chapter 3, only the Besòs and Tordera basins, all due to data availability. Now I'll be moving on to Chapter 1, which was published in Hydrology and Air System Sciences. And the main objective of this chapter is to assess water quantity at the watershed scale through the identification of spatiotemporal patterns of flow and trends of stream flow. As mentioned in the general methods, I have used the SWAT Plus tool and applied it to most of the Catalan River Basin District. And in particular, in these chapters, I focused on improving how SWAT Plus simulates the management operations. And to do that, I have collaborated with technicians from the Catalan Water Agency in order to obtain the expert knowledge on these management operations to improve the model, most notably on reservoir releases. Also, we have organized several training sessions with them so they could get more familiar on how SWAT Plus operates and all its capabilities. The model has been calibrated for stream flow using the data from 50 gauging stations across the entire study area for the period 2001-2022. First, a sensitivity analysis was performed in order to identify the parameters that affected stream flow the most. And this was done using the variance-based Fourier amplitude sensitivity test. And to see if they were impacting stream flow, we assessed the objective function Klim-Gupta efficiency, which basically tells us how the model performs. The closer it is to 1, the better. So once these parameters that were the most sensitive were identified, we performed calibration and validation. First, we randomly split the data from these first 50 gauging stations into a calibration and validation period for each station. In order to, so this random split was done to capture all spatio-temporal variability across the entire study area, because some gauging stations have a lot of gaps and temporal gaps. So this approach ensured that we captured all overall at the watershed scale. Then when we had this random split, we performed Latin hypercube sampling in order to obtain different parameter combinations. And then we used, again, the Klim-Gupta efficiency metric as well as the percent bias in order to identify the best one and obtain the calibrated model. Then to characterize spatiotemporal patterns and trends of flow, we calculated 40 hydrological indicators for each stream and year. And in these 40 hydrological indicators, some of them describe different aspects of the hydrological regime, including magnitude, frequency, duration, timing, and rate of change. Then also some of these indicators characterize zero flows and intermittency, all the way up to high flows, but also including low flows and medium. Then, once these hydrological indicators were calculated for each stream and each year, to identify any temporal trend across all these years, we used the Thielsen estimator to calculate the slope of this trend. And then we applied a Mann-Kendall test to see if this slope and this trend was statistically significant. Moving on to the results of these chapters, we obtained satisfactory stream flow calibration results. And we also used the gauging data to calculate the simulated, real observed trends. And then we compare them to the simulated ones. This was done for only 4 gauging stations, because those are the ones that have the most complete record. Because if we have temporal gaps in the data, we cannot see if there's a temporal trend happening. So we compared the ones that we could, and we found a good agreement between them. Because when trends were statistically significant, they overall follow the same direction. So this means that the model allows us to really extrapolate all the data across the entire watershed and all the simulated period. And therefore, we can obtain a very comprehensive spatiotemporal analysis of these trends. Then the analysis of these trends that we identified led to 3 main conclusions. The first one is that we identified the reduction in stream flow as well as an increase in intermittency. On the left, we have the trends in annual flow, and in red, we can see when this trend is decreasing. So when there is less stream flow across the years, of up to -6 cubic hectometers in the lower Llobregat region. Then in the middle, we have the same hydrological indicator, but standardized, which allows us to see that also, when not looking at magnitude, we can see that significant decreasing trends can be found in many smaller tributaries. Then finally, on the right, the white dots represent the percentage of the river network that dries at least once a year. And we can identify an increasing trend, a significant decreasing trend, which can be correlated also to an increase in mean annual temperature, but not to a decrease in mean annual rainfall, because there is no, for this case study and this period, we don't have a reduction in mean annual rainfall that is significant, but nevertheless, for each year, the percentage of population of river segments that dry are inversely correlated to the mean annual rainfall. Then the second conclusion is that stream flashiness, meaning the magnitude, speed, and frequency of short-term changes in stream flow, have also increased. Basically, here in these images, we see a lot of blue, which means that they are significant positive trends, meaning that rise rate and fall rate are tending to increase. So short-term changes are bigger over the years. Also, we see an increase in the number of flow reversals, as well as the annual maximum flow, meaning that even though we identified that we had a trend towards more dryness, the maximum flow extremes are also being identified. And then finally, the last conclusion that we had from this chapter is that we identified uneven seasonal response. So not all seasons have the same hydrological response. In particular, the one where it is most affected by the reduction in stream flow is autumn, which is very important because here in the Mediterranean, after a dry summer, it is very important to have a wet autumn season to replenish all the reservoir reserves. But now we are seeing that summer conditions tend to prolong into autumn. And now I will be moving on to chapter 2, which was published in Environmental Modeling and Software, and it assesses water quality now through the development of a modeling framework to assess the generation, fate, and transport of point source pollutant of domestic origins. This is an overview of this modeling framework that we developed. First, in red, we have the generation and wastewater treatment plant model, in which we simulate the pollutant loads that are being generated from urban sources, and then also the treatment that is applied in wastewater treatment plants. Then these pollutant loads are being used as input to in the pollution attenuation and transport model, which is built within the SWAT Plus model that we already talked about. And to integrate these both different models, we use the PySWAT Plus library, which is a Python library that is used both for model integration, but also for model calibration, to calibrate both models simultaneously. And this framework overcomes some of the common limitations that are usually found in water quality modeling. First off, instead of having a steady state and especially coarse solution, it is process-based, dynamic, and semi-distributed. And also, as an additional value, we have that both hydrology and water quality are being simulated simultaneously within SWAT Plus, instead of only using hydrology as an input. Then another of these limitations that it overcomes is that it can be easily applied for any pollutant that we have data of, because mostly these developed frameworks are developed for specific pollutants in mind. So this is better because it can be applied for any more easily. And finally, the last limitation that it overcomes is that the fact that it includes the generation and wastewater treatment plant model means that we do not need as much resolution in the input data regarding these domestic sources, because we are also estimating them. This modeling framework was applied and tested for 2 pharmaceuticals, ciprofloxacin in the Llobregat Basin and venlafaxine in the Besòs and Tordera basins, and we used the calibrated hydrology from chapter 1 as a basis. The reason that these 2 pharmaceuticals was chosen is because in the Catalan River Basin district, they are exclusively from domestic sources. So we had all the inputs using the generation model, and we did not have other potential inputs into the river network. Now moving on to the generation and wastewater treatment plant model and its formulation. First off, we calculate the loads in the influence of wastewater treatment plants by using the population that these wastewater treatment plants serve, as well as the generation coefficient per capita. Then we also consider the treatments that are applied in these wastewater treatment plants by considering the percentage of pollutant that its treatment removes. And then we can obtain the loads in effluents, which then are being discharged as point source into SWAT+. And this is the attenuation and transport model, which again is built within SWAT+, and it is adapted from the original SWAT+ pesticides module, which includes pollutant transport and attenuation in rivers and reservoirs. And in particular, these are the processes that are being simulated both in the water column and in the sediment layer. And these processes include degradation, sorption, volatilization, settling, resuspension, diffusion, and burial. Moving on to this PySWAT+ Python library, which was developed by some colleagues here at ICRA, and it facilitates both model integration and also model calibration. For model integration, it modifies the SWAT+ input files in order to take into account the results from the generation model. And then for model calibration, it contains several optimization algorithms that can be applied to calibrate both models at the same time. In particular, for our application, we used observed concentrations of pollutant in rivers to calibrate, and we used the optimization algorithm CMA-ES, using the objective function Nash-Sutcliffe efficiency, which, similar to the Klein-Gupta efficiency that we saw before, it also tells us how the model performs, and the closer it is to 1, the better. And on to the results, we achieved good calibration results with NSE above 0.5, which is the satisfactory value threshold, and also other metrics are within its with estimated values. Also, we can compare the observed and predicted values, and we have a good agreement. So therefore, the model is calibrated, and this allows us to look at the temporal and spatiotemporal variability in concentrations at the watershed, which is very important for the temporal variability in particular, because as we can see in the red dots, the actual observations that we have are very scarce, both in time but also in space. But the fact that in time we have so few observations means that we are not capturing this potential seasonality in concentration. So the model allows us to see that. And as we can see actually in these hydrographs, we identify an inverse relationship between high flow and lowest concentrations. That means that we see a dilution effect of high flow leading to the reduced concentrations, which can be seen in the Llobregat and Besòs basins. However, in the Tordera Basin, we actually see the opposite. So high stream flow results in high concentrations. And this can be due to different reasons. One is the remobilization of sediment and thus pollutant in the sediment during high flow events. And also another explanation could be that during high flow events, resident velocity increases and resident time decreases, meaning that not as much pollutant is being attenuated, so leading to the highest concentrations. And then for the spatial patterns that we can see across the entire watershed, it is also very important because it allows us to identify where and also when, if we consider different flow conditions, pollutants are exceeding the environmental threshold concentrations. For example, here we have the Llobregat Basin and cyperfloxacin, which we use as the environmental threshold, the value defined in the European Union watch list, which is 89 nanograms liters. And here in this image, if we have the green represents concentrations which are below this threshold, while the yellow, orange, and red represent an exceedance of this threshold. In the first image, we have the median concentrations, and we can see that the highest concentrations, the more red, is being, it's around the lower Llobregat region, which is around the Barcelona metropolitan area, which is most of the population and the pollution sources are. Then, if we compare it to high flows and low flow conditions, we can see that during high flow conditions in the middle, we have less red, meaning that the dilution effect, again, reduces these concentrations. While we see the opposite during low flow, where some reaches which before did not exceed this threshold now do. So that is very important because if the few observed data that we have is measured during median or high flow conditions, we are not capturing this exceedance of this environmental threshold which occurred during low flow, which is very important when we have long drought periods like we just had a few years ago. And now I will be moving on to chapter 3, which basically we wanted to consider more complex groundwater and surface water interactions using the SWOT Plus GW flow module in order to also assess both water quantity and quality. And this chapter, it's still a manuscript, we're still working on it, but well, yes, we're still working on it and you will see why in future slides. Basically, we applied the framework that we developed in the last chapter so that it is now entirely built within SWOT Plus, meaning that the generation model, which was previously outside of SWOT Plus and meant that we needed a Python library for model integration, now it is entirely within the SWOT Plus, so we don't need this external library facilitating its implementation. And also, as already mentioned, we modified this framework in order to also be included in the GW flow module, which more specifically, it's a physically based and spatially distributed model that calculates groundwater flow, head, and storage in unconfined aquifers hydraulically connected to streams, assuming the horizontal flow in these aquifers. And it represents an improved representation of hydrological processes over the default SWOT Plus groundwater module. Onto the attenuation and transport model, we did some modifications and improvements from the last chapter. First off, for both pesticides, which was already within SWOT Plus, and point source pollutants, which we included, we did some corrections for rivers and reservoir processes because we identified some inconsistencies between the theoretical documentation and the processes that were actually included inside the model. So we corrected those, and then we also applied them for wetlands, which were not previously included. Then also, we consider another pathway for pollutant transport, which is irrigation water, meaning that before, point source pollutants were only constricted to the river network, but now, due to this new pathway, they can also reach soils and the default aquifers, meaning that we also included for these point source pollutants the attenuation and transport processes through these compartments. Now onto the GW flow module. It did not include neither pesticides nor point source pollutants, so we added them for both. And we now are simulating transport with groundwater fluxes, for example, recharge to the aquifer or exchange with surface water, and also a transport within the aquifer itself, with advection and dispersion between cells. And then finally, for attenuation processes, we are considering first-order decay as well as sorption in the aquifer. This modeling framework was applied to and tested to the Bazosa and Turdera basins, and we wanted to focus on the comparison between how the default SWOT Plus groundwater module performed against the GW flow module. We again recalibrated a stream flow using both modules, and we perform also a new sensitivity analysis, now using the Moore screening method, and the objective functions Nasha Eclipse efficiency and Klein-Gupta efficiency. Then for calibration and validation, we applied again the random approach to split into a calibration and validation period and applied Latin per cube sampling in order to assess which combination of parameters worked the best. And then finally, after we recalibrated the stream flow, we also performed benlafaxine calibration using 8 observations of benlafaxine concentration measured in March of 2022, and we also applied Latin per cube sampling. Moving on to the stream flow results first, we did achieve satisfactory calibration results for both basins and both modules. Here in this table, we have as an example the metrics for the monthly validation, the monthly stream flow validation. And we can see that the NSE and KGE, it's all above 0.6, and also the percent bias are low. In particular, if we look at the Tordera Basin, we can see that with the GW flow module, we have a notable improvement in the NSE and KGE values, which makes sense because the Tordera Basin is very groundwater driven. However, in the Bazos basins, both results are more comparable to each other, even though with the default module, it seems that it is working slightly better. However, we can also look at flow duration curve, which basically tells us how the model performs across all from high flow to medium to low flows. And here, in this example, we have a good agreement between observed and simulated high flows and medium flows because the two lines are close together. However, in low flows, we see the model overestimates the observed low flows, which this is a common limitation usually found in hydrological modeling in basins where the low flows and intermittency are an important factor of the hydrological regime. So if we look at these flow duration curves and compare them, the ones from using the fall module and the GW flow module, we can see that they are better with the GW flow module. So the GW flow module for both basins, both the Tordera and Bazos basins, when looking at the flow duration curves, we see an improvement, especially in the high flows, but also the medium flows, and slightly also in the low flows, even though both modules overestimate these low flows. However, when we move on to the water quality calibration, we now have unsatisfactory results, even though we do seem to have a slight improvement in the metrics using the GW flow module. However, when we compare it to the results from Chapter 2, which we use the same observed data to calibrate, we have much worse results. So the question is, why are these results worse? There are several possible reasons. The first one is that in this chapter, we did not use an optimization algorithm. Instead, we used latent hypercube sampling. And this was done because the current version of SWAP Plus sometimes has an error during the simulation that it halts the simulation. And that means that if we're running an optimization process, we have to start again from the beginning and risk it happening again. However, with latent hypercube sampling, we can resume from where it stopped, meaning that I can actually finish. Second is the small corrections that we did to the attenuation and transport module. And now it is more physically based. The processes are describing exactly what needs to happen. But before, the fact that we had these slight errors meant that it was less mechanicistic, and that can result with better calibration results, even though the predictive capabilities would be reduced, meaning that if we perform validation, perhaps we would see that even the good results from Chapter 2 were not as good as we would have hoped. And finally, these concentrations are very sensitive to changes in stream flow, especially because both stream flow and loads are small. Meaning that since we only have very few observations to calibrate, perhaps by chance, even though we actually had better stream flow results in Chapter 3, but even though by chance, again, we could have a false impression of a better performance in Chapter 2. And this could be solved if we had more data to include in the calibration data set. However, nevertheless, even if we did not achieve good calibration results, we can still look at the spatiotemporal variability in concentrations and see different patterns. For example, here we have the temporal variability, and for the default aquifers module, which is on the left, we see again the dilution effect of high flows. So when we have the peaks in flow, it results in negative peaks in concentration. And however, when we look at the GW flow module on the right, we again see what happened before. So we see the opposite. The peaks in pollutant result in peaks in concentrations. And that again is due to the results already mentioned before, remobilization of sediment and reduced residence times. But now for the GW flow module, we have another potential factor that could explain that. And that is that we are now considering stream seepage as a pollutant transport pathway, meaning that pollutant is entering from the stream to the aquifer. However, with the model, this stream seepage can be up to 3 times smaller during high flow events, meaning that not as much pollutant is being removed from the stream and thus leading to these increased concentrations. We can also look at the spatial variability at the watershed scale, and even though for the default module we observed that, this dilution effect of higher flow, if we look at the whole watershed, overall we seem to have the highest concentrations during high flow events for the reasons that we've already mentioned. And most notably, for the GW flow module, which is the ones below, we can now see that we have some pollutant concentration in streams that are upstream of wastewater treatment plants, meaning that the pollutant is reaching the aquifer and then it is being transported within the aquifer itself due to dispersion in this case, and it's going upstream and areas where we would not expect to find pollutant concentrations, we are having some now, even if it's in very, very small amounts. And now I will move on to chapter 4, which is the last main chapter of my thesis, and it was published in the Journal for Environmental Management. Here in this chapter, we focus on applying a modeling approach, the developed modeling framework, in order to assess different management scenarios and in order to inform decision-making. We applied the calibrated hydrology explained in chapter 1 for most of the Catalan River Basin districts in order to test how different thinning scenarios, forest thinning scenarios, impact the water balance. In particular, first we calibrated the leaf area index for the 3 main forests found in the Catalan River Basin districts, which include the deciduous, sclerophyll, and coniferous forests. This leaf area index is basically the amount of leaves per ground unit area. And we calibrated using observed data and Latin hypercube sampling. And then, in order to simulate these thinning scenarios, first we use observed data to calculate the statistical relationship between leaf area index and total above ground biomass. And then we use the calibrated simulated data to test the relationship between the SWOT plus parameter, lay pod, and leaf area index. And then with those 2 relationships, we obtain several functions for each kind of forest that relate this SWOT plus parameter with total above ground biomass. And then to implement these thinning scenarios, we removed a percentage of this ground biomass, being -10, 25, and 50 for heavy, moderate, and heavy thinning. Sorry, light, moderate, and heavy thinning. Then, after we simulated these thinning scenarios, we looked at what happened with the water balance, so the impact on this water balance. And then finally, we performed an economic analysis. First, by calculating the marginal values of water yield, taking into account the price of water and where the water is produced. And then this, with the estimated cost of thinning, allowed us to calculate a benefit cost analysis, which is explicit in the space. So we can see where the benefits are actually. On to more information about this economic assessment, for the estimated thinning cost, it was based on average tree diameter, which comes from observed data, as well as the slope of the terrain. Then for the marginal values of water yield, we take into consideration the water consumption and price paid at surface water abstraction points. And again, we traced it to where the water was produced, taking into account that if water produced in a specific region was being used at several surface water abstraction points, the price is higher, it's aggregated. And then finally, for the benefit cost analysis, it was calculated over the recovery period for each type of forest and thinning scenario, meaning the time it takes for the forest to grow back to pre-thinning conditions. And this was done assuming a constant growth rate during the recovery period and an inverse linear relationship between total above ground biomass and the production of water yield. Onto the results, we saw that thinning had an impact on water yield production, meaning that we saw an increase due to thinning. And regarding the spatial distribution, most of the water yield production was found in the lower the headwaters of the Llobregat basin, with some reductions in the Ter basin. We also can look at percolation, which is also water that could be used as blue water, and we also see an increase in those. And this is because there's a reduction in green water, so water that the plant is using, meaning that plant transpiration is being reduced due to thinning, while evaporation of the ground actually increases a little bit. If we look again at water yield and the different types of forests, we see that the deciduous forests do not have a response to thinning, a hydrological response to thinning, while sclerophyll and coniferous forests actually have a more pronounced response. And one of the reasons that this can be due is because chlorophyll and coniferous forests are evergreen, so we see the effect during the whole year, while deciduous forests, we could only see the effect of thinning during summer and spring. And again, if we look at transpiration, we see the same thing with deciduous forests reducing a little bit but not much, and more notable reduction for sclerophyll and coniferous forests. Onto the marginal values of water yield, the highest prices of water was found in the Ter basin, which makes sense because water produced in this area is used both for Girona and the Barcelona metropolitan area. Also in the headwaters of the Llobregat, we have the following highest prices because of the aggregation of different surface water abstraction points. And for the benefit-cost ratio analysis, even though we saw that with thinning we had an increase in water yield, still it is this increase and the price of this water that is now being produced as an extra, it does not compensate the cost of thinning. As we can see in these images, where the dark blue represents when the benefits are bigger than the cost, and we only have them at very small places and not enough to compensate overall. However, we have to consider that we are only taking into consideration urban water uses. So we could also include in this benefit-cost analysis other uses such as irrigation water or hydropower, or also recreation. And these other uses could help balance it out and make the benefits higher, actually. And also, we could consider other benefits which are not related to the water balance, which would be, for example, timber production or reduced fire risk in the forest due to thinning, or other trade-offs, for example, increased erosion where thinning has occurred. So in conclusion, if we consider all these factors into a more accurate benefit-cost analysis, we could have a better understanding of the feasibility of thinning. Now onto the general discussion. Overall, in this PhD thesis, I developed and implemented a watershed modeling approach in order to characterize and assess watershed dynamics, taking into consideration the anthropogenic and the management factor for both past and future conditions. In particular, we have applied it to characterize stream flow in chapter 1 and 3, and domestic pollutants in chapter 2 and 3, calibrating the model using observed against simulated data. In this PhD, we have several advances in watershed modeling. The first one is that we fostered the involvement of the target end users, in this case, water managers. And this allowed us to improve how SWAT Plus simulates these management operations, leading to a more robust framework. And also, most notably, we have developed and implemented a domestic pollutant generation, fate, and transfer model, and also improved other for pesticides and other pollutant processes. And we have integrated it all within a single model inside SWAT Plus, which facilitates the implementation of this model. Then groundwater is very important in order to face the current and future challenges around the world, not only due to its importance as a resource itself, but also due to its interconnection with surface water. However, in most modeling approaches, surface water and groundwater are often treated independently or with simplified interactions. And that is why in Chapter 3, we applied the SWAT-GW flow model in order to characterize this more complex groundwater and surface water dynamics. And we actually saw that stream flow calibration was improved, especially in groundwater-driven basins, when using this GW flow module. And then finally, the modeling framework developed in this thesis has the potential to help assess future climate and management scenarios in order to identify best management practices, the ones that are most efficient, in order to comply with laws and regulations. And this was tested and exemplified in Chapter 4, where we assessed the impact of different forest thinning scenarios. And we looked at the impact in the water balance, as well as the economic implications of those. However, as mentioned during this presentation and in my thesis, we have several limitations that can be found in the followed approach. First off is the lack of data, both to use as model input as well as for calibration and validation. For model input, if we could get better quality data or with more resolution, it could lead to a better model performance. For example, in the application of the GW flow module for the description of several hydrogeological properties of the aquifer, we use some global data sets. However, if we had some local data sets with more resolution, it could lead to a better implementation. And also for calibration validation, as already mentioned before, we have very few data, especially for the water quality calibration. So monitoring and sampling campaigns can help us increase this calibration data set and allow us then to perform validation in order to also lead to a better result. So in conclusion, the more data we have, the better the model will perform. Another limitation is that during all the thesis, we have made some assumptions and simplifications. For example, for the generation wastewater treatment plant model, we assume that the generation per capita coefficients as well as the population connected to the wastewater treatment plants was constant, which is not true because population in cities may vary depending on factors such as tourism. So, and also some local factors, for example, mean population age, can impact the actual generation per capita coefficient, meaning if the population is older, they may use more pharmaceuticals. So if we took into consideration all these factors, it could lead to an improved methodology and as well better model performance. And finally, the last of these main limitations is the lack of actual implementation of this developed net modeling framework by its targeted end users, in this case, water managers. And even though they were involved in the development phase of this modeling framework, as we saw in Chapter 1, there is still some reluctance in actually making the most of this model, so using it to its highest capabilities. So we have to continue to communicate with end users in order to ensure that this knowledge is actually transferred and it is used for management and to inform their decisions. And now, if the tribunal agrees, I will proceed to read my conclusions. A fully integrated modeling framework was developed to characterize and assess surface water and groundwater dynamics, both in terms of water quantity and quality. The predictive capabilities of the modeling framework denote its utility to explore future climatic and/or management scenarios, thus informing and supporting decision-making in the water management sector. And now on to the conclusions from the specific chapters. Involving water managers in the co-development of watershed modeling tools results in more robust frameworks, leading to a more realistic simulation of management operations through the integration of first-hand expert knowledge. A tendency towards flow reduction and increased intermittency has been identified in the Catalan River Basin District for the past 2 decades, despite not observing a significant decrease in mean annual rainfall. Uneven seasonal trends, as well as increased stream flow flashiness, were also identified. A comprehensive spatiotemporal assessment of pollutant fate at the watershed scale reveals significant variability, highlighting the shortcomings of relying on isolated monitoring data. Integrating complex groundwater dynamics and their interaction with surface water results in an improvement of simulated watershed processes. And the implementation of different forest thinning scenarios leads to an increase in blue water, that is, water that can be collected or diverted for use. And a special explicit benefit cost assessment identifies where management actions are more economically relevant. And that is all. Thank you so much to everybody that came here today. And now on to the discussion and questions.
Okay, thank you, Laia.
Thank you.
Muy bien presentado. Now let's start with the questions. Perhaps Anna, if you want, you can start.
Okay, it's good to know. First of all, I would like to First of all, I would like to thank you to Vicenç, Laia, and Sergi to inviting me for this to participate as a member of this commission. It's a privilege being here discussing this thesis with you. I would like also to congratulate your work. You have done an excellent presentation and also an excellent modeling of work through your thesis. But I also see the lack of data that this is my part in this discussion, I guess, because during these last 20 years, I've been working with surface groundwater relationships in streams, and also I've been working with emerging contaminants in groundwater and surface water. And one of the questions that I don't understand why, but I understand why you choose these two pollutants, but I don't understand why you don't use the data that is generating the partners that you have in ICRA, because I guess you could use more, you could have more data for your models, and this could be, I think, this could improve a lot your results, because I'm certain that the first part of the thesis, the hydrological part, is excellent, and you can be proud of this. But at every chapter, you are missing more and more data, and the results are some quite, I don't know which word to use for that, but even though I think you have done an excellent work. I would like to ask you some questions. In the first chapter, you said that you assume that the crops were constant during the whole, the type of crops and the area of these crops were constant through the whole study period. And I have seen that from 2000 to 2022 to 2024, there has been important changes, significant changes in this distribution, particularly in maize. That it has been, this is one of the most watered crops, and it has been reduced at the half the surface area of this crop in Girona and in Barcelona, in your area. How do you think that this could change the results of your modeling? If you have considered these changes in the the crop surfaces and
Yeah.
whatever.
Yeah, so one of the limitations that is explained in chapter 1, actually, is that we did not account for land use changes, and we justified it by saying that we assessed if land use changes, meaning for reforestation of the headwaters, if it had an impact for this period, and we actually concluded that not. It was not important for us to the area, but we did not look at these changes in crops, which, obviously we should also include all types of land use changes for the period, because 20 years is a lot of time. And yeah, it could lead to the better data we had, the better results, but yeah.
No, I say that because
Yeah, for the
watering
irrigation.
of maize is done with groundwater, mainly from alluvial aquifers, and this is modifying also the flow in your stream and so on.
It has a big
this
impact.
is why I asked you for that. There is also, I got also another question related to this part is, to this part, and the following one is how, which data do you use to represent groundwater in your model? Because in one part you said that this data was not good enough, and I just want to understand how the model considers aquifers in stream flow and whatever.
No, Josie. So we use the hydrological gauge data from streamflow to calibrate the model. But first we had to actually do an analysis of this data, and we identified some inconsistencies in the recorded data. Since we have the full period, we have the economic crisis of 2008, 2009, and we actually saw that some gauging stations stopped recording data, all of that. So we had all this period, all these inconsistencies, and we did all this analysis for streamflow, but not for groundwater data. So yes, obviously we wanted to use this groundwater head, water depth to the water table to also calibrate, but we found that we had to do a lot of more work with the data, so we did not include it. But yes, the model would allow us to perform also calibration, especially related to groundwater head.
And could you represent aquifer heterogeneity in your model?
Yes.
Because I think this is really important, particularly when you are working with emergent contaminants or contaminants in general, because if you have changes in your aquifer, you have a layer, seal and clay layer. This changes completely your hydrochemical characteristics of your aquifer, and this can change significantly the concentrations in there, and also the relationship with the stream and whatever. How do you have the possibility to include this heterogeneity in your model?
Yes, with the GW flow, we can include those up to a point. So it's only the unconfined aquifer, so it's not like mod flow, which is more complex with more layers and all of that. There's also the SWAT plus mod flow model, but it takes more time to run, it needs more data, so this is a good middle place between mod flow and other types of these models, those integrations, and the default model, because in the default model we would not be able to integrate this heterogeneity, but with the GW flow, so it's totally distributed in grids, so we can really consider the characteristics of each grid and the hydro. Yes, we can include the heterogeneity.
I have seen, with your results, I have seen, I had in the figure 5.6 in page 80, I think the one that you represent the pharmaceuticals with the stream flow, the evolution of the... And I have seen that.
Yeah, I will arrive at it. Well, yeah, this is for... I guess you are referring to the other one, right? Or no, this one?
It's okay. I wanted to ask you why for two questions. The first one is in the observed stream flow, these daily changes in the diminution of the flow. do you know why is this produced due to punctual extraction or whatever? Or do you know, how do you explain that, the changes?
In stream flow? Well, it's,
stream flow.
yeah, I mean, it's what the model simulates. It can be due to abstractions at some points, but more of the natural regime. Because here, for example, we have from April 2022 and onwards, we actually see less peaks because it was the start of the drought period. So yeah, this is more like a response to the natural regime. Because in the Bazos, we have some abstraction, but it's not like the Ter or Llobregat basins, which are more regulated.
And are they natural? This is the observed data? Or
Well,
the
this one here is the simulated discharge. In the other one, in chapter 2, for one of those, we also have, this one here. Yeah, so here for 2 of those, we also have the observed discharge. But for the other ones, it's not a gauging station. It's just the point where we sample the concentration. So we don't have the actual observed discharge. We only have it for 50 points. But yeah, here, 2 of them coincide the same, not in the other one.
Well, related also to these figures, I haven't seen in your thesis the location or the description of the sampling points where they. I see the dots in the map, but are only surface water? Do you consider there were also data from the aquifer or?
Yeah.
Don't move to the.
No.
I know I have seen.
But it's here, I think. Yeah, here in the other one. Yeah. So basically, for water quality, in the Llobregat basin we use data from ACA, but in the Besòs and Tordera basins we actually use data that we measure ourselves, and yeah.
And I have seen that the ACA sampling period lasted like 2 or 3 months. Yeah, I have read from January to March of 2019. I don't remember that exactly, but if they have done this sampling for so long period, the data is not representative of concrete period. So the data is not comparable one to each other. So. Do you consider the moment?
Yes. Yes, it's a daily scale. So the model is calibrated at the daily scale using the daily concentrations and the daily flow. So yes.
And how do you explain the daily variability that you found describing the concentration of these pollutants? If you have 1 point.
Yeah.
And how do you explain this variability?
No, yeah, obviously we have very few data to calibrate. So yes, in chapter 2 we have good calibration results, but as we saw in chapter 3 with the same data, we had very vastly results. So it's very few calibration points. So obviously we need to increase this data set in order to say more confidently, no, the model actually performs in a good way. But the fact that it is based on actual processes, it is not, the fact that it is mechanistic, it allows us to see somehow the patterns and the variability, even though maybe the magnitude is not actually correct, but the response to the changes in stream flow, for example, they are based on a physical basis.
And how do you explain this variability? I mean, which are the drivers of this variability? The model that you use to generate wastewater, treated wastewater in your stream, or because it's just due to the changes of the river flow? both?
Yeah, mostly it seems that it's due to the changes in the hydrological regime, because as mentioned in the limitations, we are considering that both the population and the generation per capita as constants. So the fact that these are constants, the results that we now see in the model, we can attribute it to the hydrological regime, even though in reality it can also be affected by seasonality, for example, or other factors. And that is why we should continue to work on it and add this variability also in the generation model, and actually maybe assess which of this variability can be attributed to regime, to a hydrological regime, and which to the generation inputs.
And the model considers the return of these pollutants from the aquifer to the stream, because we have seen it in
Yes, actually that's why in chapter 3 we saw that we had some concentration of pollutant in stream segments that were upstream of this. It was very it was very small concentration, because concentrations are small because it's emergent pollutants and all of that, and they were infinitely small. So we put them in blue instead of green, because it's almost like there's nothing. The model tells us that there's a little bit, but it's nothing actually, because it's only due to the dispersion effect in cells, and then it gets discharged again, but it's almost nothing.
Regarding also to the relationship with the discharge and the concentration of these two pollutants, in one watershed you have seen that with an increase of discharge there is an increase, and the other the opposite. Have you think that it could be an unimodal relationship, because not usually when you have low concentration, low discharge of course you have higher concentration of these pollutants, but when you have high discharge due to rainfall events, sometimes the wastewater treatment plants are not able to treat wastewater. So you also have high concentrations when you have high discharge in your streams. Do you consider this possibility to? Because I have seen you attributed to the low trend, the low time that the pollutant is in contact with the sediments and whatever, but maybe it's caused by the not treatment.
Yeah, this is not actually included in the model now. Now there is treatment every day, for any hydrological conditions, but it could be another factor that could be included to limit. Change how the wastewater treatment plants operate also, and taking this into consideration.
Okay. I have seen that the model included wetlands.
Yeah, but we have not tested them.
Because
No, we have only included the processes, so it could be tested, but not in our case study.
Because I have seen that the model did not consider the relationship with the aquifer, only it's...
Yeah, that is a limitation of the default SWAT Plus module, which it can be implemented manually, but by default, we do not consider this. So, we only have the return flow from the aquifer to the stream, but not stream seepage, which, as we saw, it's up to, in the Turdera Basin especially, it's very important. And the fact that it was not previously included didn't make a lot of sense, so that's why we applied the GW flow module.
Okay, I have a lot of questions. I'm going through the most important that what do you said that to describe the aquifer, you take global data sets. What do you mean with global data sets?
Yeah, so for example, for the hydrological conductivity, we take it from a global data set, a map generated at the global level, because we tried to use more local data sets, but we did not really have all the data. But we know for sure that it needs to be... Yeah, I know that the global data set doesn't work, especially in the Bazos Basin, I think. It does not make a lot of sense, and it's a global data set, it has its drawbacks, but yeah. But also another limitation that I did not mention, but it was also critical, is lack of time. So that is why in the third chapter it's still a manuscript, because what I would like to do now is to change the case study, maybe find another case study where we have more data, where we can calibrate the groundwater head. So I want to do that, but I did not have time. I want to finish my PhD, so yeah, that's also a limitation.
And going to the last chapter, I would like to ask you about the shrub layer that you don't consider
Yeah.
in the model, but I think it's one of the most important related to evapotranspiration.
Yeah.
How do you consider that you could improve the model, or how do you
Yeah.
think that this could be affecting the results of what you have seen?
Yeah, this is somehow mentioned in the paper itself. And yes, it's a limitation. It's one of the limitations where we had the assumptions and the simplifications. And ideally, we would include the thinning operations all within itself. So now we had the limitation that we used it as modifying the parameter, but we want to actually modify the model so it can be included, because the way that it could be done with Swap Plus, we did not see the response that we were expecting. So that's why we followed a different approach, but we want to continue working with that and improve it. And we also could consider how the shrub then also grows after thinning, because in SWAT Plus you can have in the same, not only one type of forest, so you can have both forest and shrub growing at the same time. So it can be done. We have not done it because we've simplified it for the actual application, but in the future it has a lot of possibilities.
And just last question. Last week, the Catalan TV called me because they were worried about the pumping. Well, there was a ecologist and some groups in the Montseny Guilleries area worried about the springs the springs have been dry during the last years. And they were thinking that the pumping wells of the plants that are producing bottled water are causing this drought. Do you think, after seeing your model, that in the Montseny Guilleries, this pumping is the cause of the drying of these springs, or do you think that there are other things that this is what I think, but
I mean,
I want your expert opinion about that.
I think it's possible, because we actually include the pumping in our GW flow, not in the fall, but in the GW flow we are considering. And yes, we see the effect of pumping.
Yeah,
And
do you think
yeah.
that pumping is the worst thing there, or the
I mean,
forest
now
contribute?
that we are not in a drought period, for sure. If there's no water coming up now,
No, they have water.
Okay. Then I think it's actually the water scarcity with human-induced climate change, as then the anthropogenic impact. So it's a combination of both. But I could not say which one is the most important, because I have not studied this area in detail. But I can see it. I believe it.
Thanks a lot for
Thank
your
you.
answers.
Okay. Thank you, Anna.
So yeah, thank you for inviting me. I'm very pleased to be here again. And yeah, I found that the manuscript was very well written, very clear, very easy to read, and the presentation was the same, so very good. And I also counted 3 articles that were published as a first author. And or no, you have 3 you have 3 as first author, and you have including 1 as in preparation. Yeah. Well, anyway, it's very good. Congratulations. I have one first question about the time step. So as you recall to everybody, the hydrological regime is quite flashy. So, and you used daily time step. What do you think about, so why did you choose the daily time step?
Well, of course, it could have been easier to calibrate at the monthly time step at Calicut Dawn, but due to the flashiness of the regime and also for water quality assessments, the importance in daily changes sometimes, no? I think it's very important that we use the daily time step in order to have a more comprehensive analysis, because we can always do the means and then assess only the monthly conditions. But I think it's better to do it from the beginning at the daily step to have more resolution and to test more specific scenarios. For example, if we want to test how the different management operations in wastewater treatment plants affect the concentration of the river network, I think it's critical that we use the daily time step, because if we use estimates at the monthly scale, I mean, maybe, yes, we could have good calibration results, better calibration results, but it is not what we really want to do. We want to support day-to-day operations, day-to-day decision-making.
What about sub-daily time step, like hourly
Yeah,
time step?
sub-daily time step would also be good, so, but still, first we didn't have the data to use it, but yes, daily would be even better. And actually, technicians from the Catalan Water Agency, they want it. So it's something that yes, that if we can do it with SWAP Plus, we most definitely should.
And they have the data?
They have some data, but yeah, we would have to look into it.
Okay.
It would be more difficult, of course, because
Also,
but,
because not all processes are
Yeah.
modeled at the sub-daily time step in SWAT.
yeah.
So. Okay, then I had a question about suspended sediment. I was not able to understand by reading your thesis if you calibrated the suspended sediment.
No, we do not calibrate suspended sediment.
Why?
No.
No data? Or?
Again, yeah, data. Data and time, because, yeah, maybe you could have tried to find the data and calibrate it, but again, it would be more time, more development in the model, and yeah.
Because one of the two pharmaceutical you are modeling is very hydrophobic. So very,
Yeah.
I mean, I guess that most of his fate and transport depends on suspended sediment.
Yeah. Yeah, of course. Maybe for the water quality application, it's more that we did the development work, and then for testing, yeah, we tested it, but again, it has to be tested again in other basins with other compounds and everything. But it's the first application. Before, for the quantity, for hydrology, the model already exists, was already developed, so we could focus more on a good implementation, so good calibration, all of that. For the attenuation and transform model, since we first have to develop, then finding the correct watershed in to apply the better case study, it has been a little challenging. That's why we have used so few data to calibrate and all of that, because it's what we had at the time.
Yeah.
But yeah, of course, it should be tested in other basins with other compounds and with more data, yeah.
Yeah. Yeah, in the chapter 2, you explain that the inverse correlation between the stream flow and the pollutant concentration is not observed in the Tordera basin. So, and you explain it by several reasons, including that maybe there is increased sedimentary suspension during the flood event, and Anna said also that maybe it's because of the wastewater treatment plant flushing and stuff like this. What about groundwater? I mean, is the Tordera working differently from compared to the other catchments?
Well, in the Tordera Basin, there's a lot of stream seepage into the aquifer. So a lot of water is going into the aquifer, and then the stream itself, sometimes it's dry at the end of the lower regions. So yeah, it is very important to consider this pathway, the stream seepage, which was not previously included. But yeah, the fact that we see this inverse relationship, we don't see the dilution effect that we saw in other basins. I think it's also important to consider that first we have very few data to calibrate, so we have to take the calibration, the water quality model, still as somewhat calibrated, no? So we're still working on it. But for example, in the Llobregat Basin, which is has higher flows, we see a more consistent response as we could expect. But the fact that we have the lower flows and more intermittency in the Tordera Basin especially, I think it can also make it more challenging because it's not so we have the problems associated with water quality modeling, but also for low flows basins, no? So basins with lowest flow, it's easier to have more consistent results when we have highest flows than in the Tordera Basin, where we had smaller stream flow, and then maybe stream flow could also be improved. So it's an addition of the uncertainties. So yeah.
Yes, it was more in the chapter 3, in the figure 6.8. I don't know if you have it in mind, but my question was, how did you define low flow and high flow?
Yeah, in chapter 3, right? You said? So
Yeah.
I suppose it's, no, well. Okay, so here, no, the low flows and high flow conditions, right? Or not?
So how did you define low flows and high flows? And what, I was not, or maybe I misread it, but what duration did you use to calculate the power of the reach?
I think it's the 10th and 90th percentile to define low flows and high flow conditions, and then I use these percentiles to find a day which falls in this percentile, and then I use the data from this day, the
So
concentrations.
this is 1 day?
Yes, it's 1 day with high flow conditions and 1 day with low flows.
Okay.
In the chapter 2, where we also have the median concentrations, we have then the median, the calculated median, but then also the low and high flow conditions are also from a specific day.
So this brings new question. If you choose 1 day, is that day representative of low flow or high flow?
I mean, we tried to make it so it was, but again, we could also have done the median of several high flow days, but this is just how the data can be shown. But yeah, of course, if we only look at specific days, it can change a lot. But yeah.
Yeah. Anyway, this chapter you are working on it.
Yes.
Okay.
Yes.
Okay. Questions about pharmaceuticals. One question that I had by listening to you is, what is the half-life of the two pharmaceuticals, and how does it relate with the time the water is pumped and then irrigated again in the field and come back to the river?
I'm sorry, could you repeat?
The half-life of the pharmaceuticals.
Yeah, the half-life, we got it from bibliographical, literature reference approach.
Yeah.
Yeah. And
you know the values?
Yeah, we have it. We use it in the model, but I don't remember actually now.
But is it a matter of days, of months?
It's in days. Or yes, we take it according to days. And then it also is one of the parameters that we calibrate in the model.
Yeah.
We give it its range of change. And yes, it's one of the parameters that we calibrate.
Okay. So I like the idea of having these two pharmaceuticals because one is hydrophilic and the other one is hydrophobic. And I think you can really use them to interpret how your catchments are functioning. I mean, what is the contribution of groundwater, what is the contribution of surface runoff, and all the pathways of the contaminants with more with suspended sediment or more with more diluted and infiltrating and going with the groundwater. So that was a very good idea, I think. But you should, or I would have focused on that more in the manuscript.
Yeah.
You don't really show it in the manuscript.
Yeah, actually what would have been good also is maybe test both pharmaceuticals in the same basin, because now,
Yeah, I know.
yeah, this again was all due to data availability, because
Yeah.
we had very few observations, and finally we had to choose, okay, so we're choosing this one here and the other one here. But yeah, it would be very interesting to use them, for example, both in the Llobregat basin to see also venlafaxine and how the patterns are different from ciprofloxacin and venlafaxine. So yes, this also would be a next step forward that we could continue working on it.
In fact, in the chapter 3, you only focus on venlafaxine.
Yeah.
And this one is the most sober to suspend the sediment. And you use that pharmaceutical to test a module of groundwater.
Yeah, no.
What do you think of that?
I mean, that's why I want to find another case study to really test the development framework, because basically in chapter 3, the work was development of the SWOT plus model with modifications and all of that. And then the testing phase, it was what we could do with the time I had. But yes, obviously I want to test it with something else. I was thinking maybe if we had data for pesticides, because I also included the pesticides modifications in the GW flow module. So yeah, obviously I would like to test it with more pollutants.
And is it possible that you could test this module with like nitrates, or maybe something that is easier to measure?
Yeah, of course.
Cheaper?
I mean, well, I think nitrates were already included in the GW flow module, but we do consider in the generation wastewater treatment plant module, we can also include nitrates and other nutrients. The fact that we did not include them in any case study is because we lack the data for diffuse inputs. So we have to do a lot of estimations and simplifications in order to include them with the data that we have. So finally, we decided not to focus on it, because with so many assumptions, the uncertainty keeps adding up, and we don't know if what we're looking at it's actually based on reality or not.
Yeah, I understand.
Yeah.
Okay. In the chapter about bluing water, so I understand that the objective of the assessment is to reduce water scarcity in streams by decreasing the tree transpiration and increasing the percolation. And you give a list of benefits related to forest. And maybe I miss one, and because since the floods are rather flashy in the area, if you reduce the, the aim is to infiltrate more water.
Or not only infiltrate, also surface water. The water yield that we're using here is just surface runoff.
Yeah,
so
okay,
increase,
exactly.
yeah.
So if you increase the surface runoff, what is the impact on the floods?
Yeah, we are not considering that. We should also look into it and use it as another trade-off. So the trade-off could be, yes, we have more water to use, but it could also have negative consequences if it is too much water. But
damages related to.
Yeah, I think it's another thing to include in the benefit cost analysis, because right now we're just assuming only urban water uses, and that's it, and no other benefits and no other trade-offs. So we really need to focus on a more accurate benefit cost analysis, which would be more interesting if it includes all the possible factors that are affecting it.
And did you observe increases in the discharge peak?
We did not look actually at peaks, at daily peaks. We only looked overall if the water yield increased. And we looked at these estimates because, again, we simplified the approach. Yeah. But obviously, it's very important, especially at the local places. It can even be detrimental to have thinning, even if downstream they could use this water at the highest price, and it would be very beneficial in this sense, but not if it damages other parts of the basin and other stakeholders. So yeah. yeah, it's something that it needs to be considered. And the fact that the model allows us to do a spatially explicit approach, it can really allow us to see where the impact is beneficial, where it is detrimental, and how can it be optimized so it's the best for everyone. Yeah.
And what could be the impact on pollutant transfer?
Pollutant transfer
Yeah.
in which context?
In the context of thinning forest.
We did not look into it. I mean, I don't know about a lot about it, but I mean, it can also, if we use it for different aspects, so we could consider for one, the impact on the water balance, but also how this impacts, for example, the nutrients concentrations, and then do a joint benefit cost analysis to see the impact of everything, but we have not considered it here.
Yeah, and I was also wondering if the thinning could have an impact on the soil properties and then change the hydrological behavior.
Yes, I suppose it could. I'm not an expert on this part, but yes, I guess also other how the forest responds to this thinning, for example, with more shrubs and all of that, it can, I guess it can change the composition of the soil and then also the impact it has on water balance or water quality and all of that. So yes, it's something that it needs to be considered. And with the model, it can be. We can simplify it as much as we want, but we can also add the complexity as we need.
Yeah, and then I had, yeah, as Anna already highlighted, I was surprised by the small amount of observed data.
Yeah.
And okay, I understand it's not your fault, so don't worry. But if you, so I understand that pharmaceutical measurements were made during above median or high flow. What would you expect regarding improvements of the simulation if you had measurements during low flow as well?
Yeah, if we increase the number of measurements, for starters, we could have an idea of the expected seasonality we would expect in these concentrations patterns. So if we already know from observed data, it's more easy to see if the model is actually performing as it should. The fact that it does not exist, well, it's a limitation because right now, obviously, when there's low flow, concentrations are higher because it's more concentrated everything. So we know that it's a problem, but we are not quantifying. So now the model allows us to at least see it a little bit, what the pattern that we should expect is. But of course, first we need the actual observed data, first to calibrate the model and then validate that what is happening is correct and see if we have to maybe adjust the processes that are being simulated. See, okay, so we're considering this one, but not this other one, which is actually more important due to this. But yes, first we would need to have this data in order to first see if the model is performing well, and then to calibrate and validate it, yes, of course.
Even during low flow, for small concentrations.
Yeah.
Okay, and besides temporal variability, there is also spatial variability, and I see that the sampling station in the 3 catchment are located downstream. And so you have, aside of having few data, all the data are downstream.
Yeah, this is because in the Vasos and Tour databases, we use data from our sampling campaign. And they are so close together. Okay, so here we can see it. So yeah, because we wanted, in this specific campaign, we wanted to see if we could see some attenuation between those 2 points. So that is why they're so close together. Of course, if we now performed another sampling campaign in order to obtain data to calibrate this model, it would have a different distribution. Of course, we would try to see more at different places, but here it's the limitation of data that we had and the time that we did not have the ability to obtain more data or a new case study, which already had more data itself. So yeah.
Okay. And also related to data, but as input data. So an assumption was that an assumption of the pollutant generation module was that 97% of the population of Catalonia is connected to wastewater treatment plant network. Is this true in the upper part of the Llobregat, Bezos, and Tordera?
We have not looked into it. We only see the overall. Maybe it's not as much, but especially in the lower Llobregat and Besòs, I think most of the population, almost everyone, is connected, and it's where most of the population lives. Other places, yeah, they may not be connected, or maybe they are, and we are not considering in the model because it's outdated data, but we don't really expect it to have a big impact because most of the pollution generation is concentrated in around the Barcelona metropolitan area. So, and we are covering those main focus of concentrations.
Okay, and I have a last question about the, along your thesis, you stressed the need to involve water managers in the modeling. And you also say that there were, so you found reticence.
Yeah.
So can you explain us?
Yeah. So
why are the water managers
so
to use these models?
Yeah. We involved them during chapter 1, as we saw. We had several training sessions with them, and not only training them into using the model, but also updating them on how everything was working during the development. So we tried to involve them as much as possible so they could adapt this model as their own, and they could use it to actually support their decision making. But we have found that they are somewhat reluctant into actually using it because the model that they used before, it is not as complex as SWOT+. It uses the natural regime and all of that, and they do many assumptions in order to account for the management factor. But since it works, they are somewhat reluctant into using a more complex model, which would require more work, more knowledge on the model itself. And they are not really using it. So they are using it for specific things, no, sometimes, but they don't realize all the other parts of management that it could help with. So we need to try to make it clear all the capabilities of the modeling framework and how it can be used and how to use it, or how to tell us what they want so we can actually implement it. So yeah, it's still an ongoing relationship. And because of course the final objective is so that it can be used in order to support decision making and improve how we manage these basins and actually do something. Not only for research purpose, which is also good, but we actually wanted to have an impact. So yeah.
Thank you.
Okay, thank you, Lorraine. So now it's my turn. I will try to do most of the question in English, but there are some parts that I will do in Spanish because I want to explain. I want her to understand better what I want to say. First comment is congratulations, Laia. I mean, you are here with a thesis based on a company of publications. I suppose that international mention because you went to Colorado. I have followed your thesis because we met each other in the SWAT conferences. So now I'm going to ask some questions in order to improve and some tips and things for the future. But first thing is that the work is done. I mean, we are not evaluating your thesis because your thesis has been evaluated by external reviewers with the paper. So, I mean, you have to be very happy with the work that you have done. But my first question, and it's kind of a general comment, is that I don't see very well what is the connection between papers. I mean, I would like to know how, I mean, if this thesis is what you were thinking from the beginning, what is the framework of this thesis, the connection between papers, I don't know, this is something that you have to do based on task of a project, you have chosen what to do and where, because the idea of I have no data is okay, but in some sense, I think that you have been chosen where to go. So you can decide case studies and this type of things or not. I mean, I need an explanation about how was the way of your thesis.
Yeah, so my project changed a lot from the beginning to what it is now. So the first idea was to use a modeling approach to quantify water quantity, water quality, which was, I was first thinking more of nutrients, for example, and then also to account for hyporheic dynamics, which were not included for different reasons, but this is another thing. But the original plan, it was that. And then also quantify water quality, quantity, and then also include some future climatic scenarios in order to support decision-making at policy-relevant timescales, so up to 5-10 years, which would be helpful for water managers to help produce their planning and management plans. So that was the original idea.
So his paper, including more things.
Yeah, so one paper for water quality, one for water quantity, and one for, for the decadal time steps. Okay. So that was the original idea. However, when I started working with SWAT Plus, I saw that it was very difficult, so I had to do a lot of previous work before I had the working model that I use in chapter 1 and 4. So I saw the lack of time again, and I had to adapt. So then the first paper was supposed to be also water quantity, but including the GW flow and the more complex groundwater dynamics. But finally, due to the way it worked, I only included the surface water. And then to do something else, I did the analysis of the spatiotemporal patterns and trends, which was really interesting. And then for the second chapter, which was supposed to be the water quality, it was all the development of the framework, but still we did not include the GW flow module. We did not have the time at the moment, but we did include then in this chapter 3, in this new chapter 3. And then instead of using this climatic climatic scenarios for the last chapter, we use instead an example of the management scenarios. So that is why this fourth chapter is now included. So yeah, that's more or less how it changed.
Okay, so everything was based in your own decision or your both decisions. I mean, there were no tasks under a project, and that's why I went to Tordera Basin. No. I used this pharmaceutical. Everything was chosen by you.
Well, no, not exactly. So, yeah, the Catalan River Basin as a whole, first I wanted to use the whole study area, and I did for the first chapter, more or less, because in other regions we did not have enough data to really have good model performance. But for the quality aspect, we had to decide yes, where and for which contaminants, depending more on the data that we already had, because we could not have more data. We did this sampling campaign and we used it for the Benla vaccine, but we really had to look at where the data was, and most of the data was around the Llobregat Basin. So that is why in chapter 2 we used the Llobregat Basin with data that we have from the Catalan Water Agency. And then we complemented with our own data for the other basins. But the decision on which basins to use, it was all due to the data availability. So we knew from the beginning that we wanted to apply to the Catalan River Basin District, but it was very open on to which basins specifically. And it was, at the end of the day, depending on the data that we had. Yeah.
Okay. Mi impresión es que ha sido un poco masoca y kamikaze en ese sentido. O sea, yo creo que el potencial de todo lo que has hecho podría haberte dado para muchísimas más publicaciones de las que has sacado al complicarte mucho la vida en determinados aspectos. ¿Vale? O sea, yo creo que podrías, por ejemplo, del primer paper, creo que podrías haber hecho muchos más análisis en base de lo que ya tenías y prácticamente solo eso ya te da una tesis doctoral y un compendio. ¿Vale? Pero bueno, now if you want, we can follow every chapter in order to see some questions and ideas that I have. I mean, One important thing is that I haven't seen in the manuscript or in the supplementary material the final value of the calibrated parameters of the SWAT model. Okay, because you were trying to do something very difficult, that is to simulate the observed stream flows in a highly regulated basin like the Catalonian River Basin, etc. I haven't seen the final values of the SWAT parameters in the papers or in the documents. Or
Yes, that is true that for the streamflow calibrations, we did not provide the final ones, that's true. We did for the quality ones, for the attenuation and transport and generation models. We have it in a table, but yes.
But why? I mean, I suppose that
Yeah.
you have a lot of basins, so because my question is because
In the first chapter, we have, I think, 5 different SWAT plus models. Yeah.
I'm worried about the range of the parameters that you have used in
Yeah.
order to calibrate your model, because as what you are doing is very difficult, you have to increase the range of the parameters in order to obtain good observed stream flows. So, for example, I saw that the curve number in the sensitivity analysis, I don't know what
No,
you did.
yeah, that's because
You
in the
use minus 50% plus 50%. That's something
but
real.
that-
Do you know what I mean?
Yeah, I know what you mean, but that we only use it for the sensitivity analysis because we wanted to. It was not as important, so it made a physical sense in that. But if it was sensitive, we only wanted to identify if it was sensitive.
So for
Then,
the calibration, you
we
reduce the
reduced
range of the parameters?
Yes, I think at least up minus 25% for sure. So we reduced it a lot by half.
Okay, so let's focus first on the first paper. Why did you use the floodplain map? What was the reason why it improved the SWAT input data, or why? What is the reason?
We used it because we had it and because SWAT Plus allows us to use it, but we did not try to look whether it resulted in better calibration results. So we only.
How do you use the floodplain map in order to prepare the SWAT model?
Yeah, when we are building the model, you use it as a raster map, and then it separates it into different HRUs. So even instead of having one landscape unit per watershed draining to a single stream segment, you have two, the upland and the upstream, and then water. So since it's semi-distributed SWAT plus, if you don't use a floodplain, all the water is being generated at the HRU level, and then it goes directly to the stream. But with the floodplain, the upland HRUs, the water first goes through the floodplain HRU. So,
okay. Relate to the human modifications that we have in the first paper. You use wastewater treatment plants data, industrial discharge, abstractions. What is the temporal scale of that information?
Yeah, we have assumptions made for that. So we have for the abstractions, for example, we have the average annual amount, the volumes. And then we assume that it was every day it was the same, so it was constant in time. So yeah, and for the wastewater treatment plant data, we also assume the same. So the population and the generation, it's all constant. So yes.
You have kind of order of magnitude, so it's more or less. That's the point, that you are trying to obtain daily stream flows based on order of magnitudes. So that's why I say that it's very difficult what you are trying to do. Do you have any reason why your validation statistics are better in the validation period compared with calibration period? Because I don't know if you have checked that in the model, the validation is better in terms of statistics. I mean, did you check if there are much more water in the calibration period rather than the validation period, and these type of things?
We prioritize the results that were better for validation, but it couldn't be done the other way around. But since both results were good in both periods, yes, we prioritize a little bit for the validation period, which means that it's not really a validation period. So maybe we should also test it again with new data and use it as a true testing period. But yes, so.
Because, I mean, you take all the flow stations, and in all the flow stations, some period were for calibration and validation?
Yeah.
Or you take some station
No.
for calibration and others for validation? No, no?
No, each gauging station has 70% of its data used for calibration and 30% used for validation. And yes, it is randomly allocated for each gauging station so that we capture all spatiotemporal variability as a whole. No, so maybe one station, the validation period does not capture all variability or all climate variability, but since the gauging station below it does, as a whole, we are capturing it, so yes.
Okay. And relate to the first paper, I mean, so the idea is that you want to simulate the observed stream flows in all the Catalonian river basins just because you want to complete the daily stream flows, I mean, the granularity of your information, no? That's the idea of that model?
Yeah, yeah. Well, and also assess water quantity as a whole, no? So to use it as a basis for other things we have done for chapter 2 and 4. But
I think that, I mean, the potential is more related in the comparison between the natural regime and the artificial or real one that you have simulated. Because, for example, just checking this trend of stream flows that you did in the first paper, you don't know, I mean, ¿quién es el culpable? I mean, we are talking about the human impact or weather. I mean, you can do that very easily. Just running the same model, modifying weather. I mean, you have included in the basin all the human things. Let's remove that and let's simulate again. These type of scenarios are very easy to do and give you the idea of what is happening. Climate change, human impact, these type of things. Or another example, another idea that you can use in order to do a lot of different things. I don't know how does it work in the river plans here in Catalonia, but in the rest of the demarcaciones hidrográficas, I mean, the estimation of environmental flows. Estimation of environmental flows is based on the natural regime of the rivers.
Yeah.
So what we are doing in Spain and in the other hydrographic demarcations is to obtain, or what they are doing is to take the data from SIMPA. SIMPA is a national hydrological model on a monthly scale. They don't have daily. They then try to disaggregate to daily on kind of a strange thing, and they evaluate or they calculate environmental flows. You have a better model in order to do that. I mean, you can check what are the environmental flows that they are calculate. What is the difference with your model, if they are okay or not? I mean, there are many different scenarios and ideas that you can do just only using your first paper and your first idea.
Yeah,
okay?
Actually, outside of this thesis, we actually compared how SIMPA and Sacramento performed against SWAT, and we found that SWAT Plus performed much better. But again, technicians from the Catalan Water Agency prefer to use SIMPA because it's what they are using now and it works, but this works better, so that is why we need to...
But you have to give them what they want. I mean, you can use SIMPA. I mean, you can use monthly stream flow from SIMPA in order to calibrate some points. I mean, I understand that because it happens in the other places. Okay, so relate to the second paper, the paper published in Environmental Modeling and Software. So if I have understood well, you are estimating a volume per person and day. Okay, no, you say around 250 cubic meters per habitant and day. Yeah. So you know more or less for each wastewater treatment plant what is this amount of volume. And then the problem is that you have no data. I mean, one of the questions is, I mean, because she asked about, I mean, why these two are different. You say because the data is that, but then at the same time, you choose one for one basin and the other for the other basin. They are not both in the same place. And also, you are choosing, I mean, you are trying to justify that your model is working. I mean, why you go to a big watershed with 21 wastewater treatment plants instead of going to a smaller watershed with one waste treatment plant or two where I have more information? Do you know what I mean? There are easier ways to justify your model.
Yeah, I guess that we wanted to, since from the management perspective, it is important that we quantify all the basing in order to have the complete picture. I guess we wanted to try to do that, but yeah, we have the limitation that the data, yeah, of course.
The problem is that you are showing the limit, that the limitations are so big. I mean, you were
Yeah.
talking about subdaily. I mean, SWAT plus subdaily is not working right now, so we cannot do that. So I mean, you are going with the SWAT model to the limit of what we can do with the
Yeah.
model. Do you know what I mean?
Yes, yes.
So the other point is that you have 8 samples, and then based on that, you have a parameter that is the amount, the grams or nanograms or whatever per liter. So you have also calibrate the amount of pollution that you include to the wastewater treatment plant. Is okay because you don't have the data. So
Yeah.
the only data that you have is the amount of this thing in the river,
Yeah.
and you don't have more information. That's
Yeah.
also the efficiency of the primary treatment, secondary, tertiary. Also, this is another parameter calibration.
No, yeah, no.
So you are calibrating everything. Do you know what I mean? So
Yeah, in the ideal circumstances, we would first calibrate the generation model and wastewater treatment plant. First, if we have data on wastewater treatment plant influent before sanitation, try to use this data to calibrate. And then also for the treatment, especially for the data in effluents before being discharged. And there exists some data here, but not for pollutants that we could easily apply, because we have a lot of this data, for example, for nutrients, which would be great if we could apply it. But since we don't have the information about the diffuse sources, finally, we decided to use only domestic pollutants in order to limit this uncertainty. And yes, we have uncertainty at the generation, but if we used some pollutant where we have data to reduce this kind of uncertainty, we would have uncertainty in other parts of the model, so it would complicate things.
but I don't know who is in charge of the wastewater treatment plants, the Agencia Catalana del Agua.
Yeah.
I mean, they don't measure how much goes to the treatment plants, because I'm sure that they don't measure what they throw, but what the inputs, for example, to the wastewater treatment plants.
Yeah, we have some measurements for some pollutants, but not for this, for ones that were specifically only domestic sources.
Because how
And then
do
we
you
had
know,
data in
how
the
do you
ocean
know
streams.
that the amount of contaminant that you are including to the wastewater treatment plant is okay, more or
Yeah.
less? Do you know what I mean?
Yeah, the fact that we do a simultaneous calibration of both the generation model and the fate and attenuation. So yes, we are calibrating both at the same time with the same data, and yes, uncertainty keeps adding up. That's why in the paper we mentioned that we would want to have more data in order to have not calibrate both models independently, because that is not what we want to do, but to do a multi-objective calibration using both data. So trying to maximize both, yeah, it's
But
complicated.
Again, you are trying to do something much more difficult. I mean, don't do multi-objective. Try to go from small to big. Do you know what I mean?
Yeah, also, yes. At least at the first time to test it, the model's capabilities, and then it can always be...
As you have only around 10, 18 observed samples, and she was talking about something interesting, because the relation with suspended sediments. I mean, do you know LOADEST, or perhaps machine learning, no, because you don't have too much data, but perhaps, do you know what is LOADEST?
No.
LOADEST is kind of a very easy software that is from the USGS, and they give you some equations that relate flow and sediments, but perhaps you can try to find any type of relation with what you don't have data, with something that you have data, in order to obtain kind of simulated more information, so you calibrate your model based on this continued data. This is something that a lot of people do in their papers, and it's something that perhaps you can use in order to, I mean, when you show the calibration that you have only 4 points,
Yeah,
type of things,
yeah.
do you know what I mean? So perhaps you can use kind of an intermediate way of creating your observed data. based on these relations with what you don't have the data, with something that is easier to measure, like, for example, the suspended solids or something like that. Relate to the SWAT plus DW flow. I mean, the paper is still on work. I mean, you didn't submit to any.
No,
any
because
journal.
again, I want to change the case study to make it easier because we are really reaching the limits of what this case study can give us. So
That's
yeah.
what
Yeah.
I'm trying to tell you. I mean, so you finish the work.
Yeah,
You
yeah,
have
yeah.
been working in that a lot of months, and now is when you want to change the case study. Perhaps you have to do that, but before.
No,
starting
I
or-
mean, I've wanted to do that for a long time, but also I needed to finish my PhD.
Okay.
And if I started a new case study, maybe I could have finished it very quickly and ready for the defense. But maybe I could have found some issues and then just more months. And finally, we decided to prioritize my PhD defense. And then we can always keep working on the model.
Okay. So, I mean, in that sense, same thing. I haven't seen in the figures. Where are the wastewater treatment plants? I mean,
Yeah.
we have seen where you take the samples, the flow stations, but where are the wastewater treatment plants?
Yeah, they're in the, well, for example, here in this, they're very small here, but they are the gray dots, yes.
Because it's, I mean, what they say, try to find a small
Yeah.
basin in the big basin in order to demonstrate that the model is working. You don't need
No,
to
yeah.
go to the extreme or to the more difficult case study.
Yeah,
Just,
that's true.
I mean, when you modify the equations, I mean, this is a word that you can publish. Just demonstrate in an easier case study.
Yeah, that would be
Because
ideal.
that way, I mean, you don't have to calibrate, I mean, because you are calibrating everything.
Yeah, and if we're missing some data, it's easier to try to complete
Yes.
the record if it's less data
And you
to
can
obtain.
check where are the
Yes.
problems,
Yeah.
because if you go here, I mean, the problem can
No,
be
yeah.
everywhere.
Yeah.
Okay. In this case, you have been comparing SWAT plus or aquifer module with SWAT plus DW flow. But you have calibrate again, for example, the generation per capita coefficient. So in one model, you are obtaining double grams per habitant and day compared with the other. I mean, if you want to see
Yeah.
which model is better, why don't you maintain constant la porquería and then you check what model is better? Do you know what I mean?
Yeah,
Because
yeah,
you
yeah.
are modifying everything. They are not, you cannot compare that.
Yeah,
Do you know what I mean?
Yes. Yeah, we reduce the change, no, the allowance of plus minus. But yeah, that would be a very interesting way forward to just compare the models, the
Yes.
SWAT plus models, and not the generation. Yeah, keep it as constant. That's
Because
true.
if not, you are including different
Yeah.
water quality. Okay. I mean, the use of piezometers. I mean, if you use GW flow, and we were talking about how perhaps some pollution is going from the aquifer up. I don't know how deep are the levels in this area, or if they are high or not.
Generally, in the alluvial aquifer, they are tending to be higher. So
Okay,
yeah.
so it has sense that you have some.
Yeah.
Okay. I mean, some question when I was so let's finish with the last paper because you were jumping from one idea to other. One thing that is important for me. So the last paper was prepared based on the hydrological model that you did in the first paper.
Yeah.
Okay. So you did a calibration, better or worse, but you did the calibration, you have that model, and then you try to improve with the leaf area index, no? You calibrate other parameters relate to the leaf area index.
Yeah.
I'm not sure, but I think that if you modify parameters of the leaf area index, at some point, you are modifying real evapotranspiration. So after modifying leaf area index, you have to go back to check,
Yeah.
SWOT check or stream flows, because I mean, in Murcia, that is semi-arid place where the real evapotranspiration is 95% of the hydrological cycle, for sure that you have to do. I don't know here, but here we are talking about Mediterranean areas where the real evapotranspiration is a very important part of the hydrological cycle. So perhaps with the movement that you did after the hydrological calibration, you are also modifying the stream flow.
Yeah.
So perhaps the model is not correct, or you checked that before?
No, we did not check, I think. No, but here also what we could do again is a multi-objective calibration. but yeah, or
Okay, and I think that that's all from my side. Congratulations
Thank
again.
you.
And what is supposed that we have to do now? We have to
do the paperwork, so.
Okay, so thank you very much, Laia.
Thank you.
And we keep in contact. Okay. No, es que yo recuerdo otras tesis que ahora solamente le decimos la nota y llegan.